I conclude the theory of work, energy and power with this fourth module on power. In Module 5, I will concentrate on examples with the aim to prepare you to successfully answer questions in the exams. If these modules are of any value to you, please subscribe to my free Get a Grip on Physical Science YouTube channel at the end of this video. It's free of charge, but will help me to continue to record and distribute these videos, and it will help you to stay updated with new video releases and additional videos with examples to prepare you for the exams. Module 4 will cover the definition of power as well as the calculations of power. Power is defined as the rate at which work is done. Now, when we read the word rate, you must know that we divide by time. So in this case, we want to know how much work is done per second. So the formula that we use is this one. The P represents power, it's a capital P, and we measure this in watt. The capital W represents the work done in joule, and the delta T represents time, or the change in time, and we measure time in seconds, and we have to use the abbreviation of a small s, never your own abbreviation. At this stage, there are two things that I would like you to take note of and remember. The first thing is, if you look at the unit of power, we measure power in watt. And according to this formula, you can see that watt is equal to joule per second. Now, they often ask questions where they expect you to know this. So they want you to know that watt is equal to joule per second. So just take note of it and remember it for now. And the second thing is, the power that we calculate in mechanics is the same as the power that we calculate in electrical circuits. So when we get to the electrical circuits topic, remember that they can actually ask you to calculate the mechanical power and apply it to the power that you use in electrical circuits. So let's look at a few examples. A 600 kilogram motorboat accelerates from rest to reach a velocity of 22 meters per second in 8 seconds. Ignore friction and calculate the power of the engine of the motorboat. To calculate the power of the engine, we need to know what work was done by the engine, and we need to know in what time. Now, the time is easy because they said that the motorboat accelerated in a time of 8 seconds. And we can calculate the work done by the engine because we know what the initial and the final velocity of this motorboat is. Now, you can use any method to calculate the work done by the engine. I'm going to use the Work-Energy Theorem because it's easy to calculate the change in kinetic energy here. We know the initial and the final velocities, we know what the mass of the boat is, and we know that the only force that does work here is the force of the engine. So the net work is the work done by the engine, and that would be equal to the final kinetic energy minus the initial kinetic energy, which is 0 because the motorboat accelerates from rest. And then we see that the work done by the engine is 145,200 joule. So if we calculate the power, then the power is equal to 145,200 divided by 8 seconds, and then we will know the amount of energy used per second. So the power of this motorboat engine is 18,150 watt or joules per second, or 18,15 kilowatt. Here we have a slightly different example. A borehole pump is used to pump water out of a borehole. The pump must pump water from a depth of 15 meters to the surface at 80 liters per minute. Calculate the minimum power that the electric motor should have to pump the water to a dam on the surface. To calculate the power of the electric motor, you need to know the work done by the motor and you need to know in what time. Now with these borehole pump examples, there are two things that you have to know. The first thing is the kinetic energy of the water that enter the pipe is the same as the kinetic energy of the water leaving the pipe. So the kinetic energy remains constant. The speed remains constant in the pipe. The second thing that you have to remember is that the mass of 1 liter water is 1 kilogram. We start by assuming that the kinetic energy of the water remains constant. Now you can use any method to calculate the work done by the electric motor. Because I used the work-energy theorem in the previous example, I am going to use the work done by non-conservative forces in this example. There's only one non-conservative force here, so the work done by non-conservative forces is the work done by the pump. And that will be equal to the change in kinetic energy, in this case 0 because the kinetic energy of the water remains constant, plus then the change in the gravitational potential energy of the water. For this example, I take the 0 reference point as the bottom of the pipe. Then the water needs to be pumped 15 meters higher than that initial reference point of 0. So the initial potential energy will be 0, and then we can calculate what the final gravitational potential energy of this water is. 80 kilograms for 80 liter of water multiplied by the gravitational acceleration of 9.8 multiplied by the new height or the final height of 15 meters above the 0 reference point. So the work done by the pump is 11,760 joule. The power of the electric motor of this pump is then 11,760 divided by 60. We know that that 11,760 joule was the energy or the work done to lift 80 liters of water per minute. So we divided by 60 seconds to know what the amount of energy, joule energy, per second is. And that gives us 196 watt or 196 joule per second. This is a very important variation to the usual power calculations. We know that power is the rate at which work is done. Now, work we can calculate with the work formula. So if you look at the yellow part here, you can see that it actually represents the velocity of the object. The rate at which displacement changes is the velocity or the average velocity of an object. So we can rewrite this formula as the force multiplied by the average velocity. But a tip, they will give you in the written piece an indication that this object has a constant speed or a constant velocity. So always look out for a constant velocity. The formula is given to you on the information sheet. The pleasure boat engine delivers a power of 150 kilowatt as it travels through the water at a constant speed of 2 meters per second. Calculate the magnitude of the force exerted on the water by the engine's propeller. Important to notice that the speed is constant, and they gave us the power of 150 kilowatt, and they ask us for the force exerted. So the formula, the average power is equal to the force times the average speed. We know that the average power was 150,000 watt, and that would be equal to the force multiplied by the speed of 2 meters per second. So the force here is 75,000 Newton. No direction because they asked us only for the magnitude of the force. A motorcycle travels at a constant speed of 110 kilometers an hour in a westerly direction on a rough horizontal tar road. The motorcycle's power is 40 kilowatt. Calculate the kinetic friction that acts on the motorcycle. So important again to notice the constant speed. Now for the motorcycle, the constant speed implicates that the net force on the motorcycle is equal to 0. There are two forces here, the force of the engine and kinetic friction. The force of the engine is in a westerly direction, and the kinetic friction then in an easterly direction. Now because we're working with forces here that are vectors, we have to choose a direction. So we're going to choose the direction of the engine, the applied force, as positive. So we choose west as positive. The power of the motorcycle is given, it's 40,000 watt, and the constant speed of this motorcycle is 110 kilometers an hour. We need that in meters per second. So to convert from kilometers an hour to meters per second, you divide by 3,6, or you can just say that you change the 110 kilometers to 110,000 meters divided by 1 hour, so it's divided by 3,600 seconds, and that will give you the same answer. So if we substitute into our formula, the power is 40,000 watt. The velocity or the speed is then 110,000 meters divided by 3,600 seconds, or you can just say 110 divided by 3,6. So the force of this motorcycle engine then is 1,309,09 etc. Newton. We cannot round off yet because this is not the kinetic friction. They asked us for the kinetic friction. But we know that the motorcycle travels at a constant speed, so we know that the net force acting on this motorcycle is 0. And that's the force of the engine plus the kinetic friction, and that's equal to 0. We can calculate the kinetic friction. It's equal to negative 1,309,09 Newton. The negative we can interpret as east, and we can round off to 2 decimal places. So the kinetic friction then is 1,309,09 Newton east. If you are an educator that would like to inquire about the use of these PowerPoint slideshows in your classroom, you may contact me at lawsandwonders@gmail.com. Please indicate if this topic was useful to you or not, and subscribe to my YouTube channel in order to stay informed about the release of my most recent videos.